Hello, guys. We're going to be covering the Octet Rule today, section 8.2. I have no idea why the camera's not working here, but we're just going to keep on trucking. Okay, so we are talking about Octet Rule, section 8.2. How are electrons organized in atoms is part of our introduction, and it starts talking about graduation, a very special time. You know, when you guys walk out during graduation, oh man, I just love to just look at y'all's faces when you guys are walking onto that floor at the State Farm Arena. The pride in your face is it's priceless. It's priceless. You know, you guys just look so proud of yourselves. Your parents are proud. Everybody's yelling and clapping, and you guys look so nice in your pants and and your dresses, and you have all this pretty makeup, and you're oh man, it's very, very special. I love graduation. I don't go to all the graduations. I try to, but sometimes we get the early graduation, 8 o'clock graduation. Like, why can't we switch and get like the noon graduation? But anyways, I do like going to graduations. It's fun. All right, who's gonna help me with the introduction? Irvin, you want to help me?
Yes, ma'am.
Thank you, sir.
Graduations are exciting events in one's life. The processional, the ceremonies, even the speeches can be handled because this marks the end and the stage of the life and the beginning of another one. The ceremony itself is challenging for those organizing it. There are just enough seats on the stage for the graduates. How do you avoid getting too many people in a row and not enough in the next row? Someone is stationed at the end of the row to count the students as they enter. Only so many are allowed to go into a row, and then you begin to fill the next row. Electrons as atoms behave the same way. There are rules that determine where electrons go and compounds.
Thank you, Irvin. Appreciate it. So, anytime, when you're filling in the rows at graduation, and this is going to happen for everybody, I have every faith that every single person in this class will be graduating in a couple years. Okay. But either way, when you guys are sitting down or about to sit down, you're walking in, you go into the rows, there's a teacher, there's somebody, a coach there telling you, okay, count, because he's counting, or she is counting, and say, okay, that's it. You start the next row, because you don't want that awkward moment when there's too many people per row, and then you got somebody who's left out who doesn't have a seat. No, that's a big boo boo, right? So there's a person there to tell you, hey, this row is full. You need to start into the next row, so we don't have that awkward moment, because there's only a certain amount of seats per row, and once you've met that capacity, plus you need to go into the next row. The same thing happens for electrons, right? Once an energy level has completely filled, those electrons are going to start, the next electron is going to start a new energy level, right? And when you have your final outcome, that outer energy level can be full if you're a noble gas, or it could be partially full, right? If you are a noble gas, group 18, right? Group 18, uh, where you have helium, where you have neon, and all of those guys, group 18 is special. Once all of the electrons are in their proper energy level, this group right here, neon all the way to radon and element 118, that outer energy level is already going to be full. These guys are going to be what's known as stable, right? And the reason why it's stable is because they're going to have those 8 valence electrons in that outer shell. Okay? If you don't have 8 electrons in that outer shell, you are not stable. Okay? So elements will have a tendency to lose, to gain, or to share electrons to make that 8. All right? So let's get started. The octet rule. This is where we started talking about those noble gases. Those everybody wants an electron configuration similar to a noble gas, right? The noble gases are unreactive because of their electron configurations. And they give you an example. They show you the electron configuration for the noble gas neon. The noble gas neon will have a electron configuration of 1s2, 2s2, 2p6. Now, if we're talking about the outer electrons, we're talking about that last energy level, okay? For neon, it's energy level 2, right? Energy level 2. In energy level 2, you got 2 different orbitals. You have the s orbital and the p orbital. For the s orbital, it's going to have 2 electrons. For your p orbital, it's going to have 6 electrons. And when you add those up, you're going to get those 8 electrons that you need in order to have that stability that these noble gases have. And it says here, neon has a full outer shell and cannot incorporate any more electrons into the valence shell. And remember, that valence shell is the outermost energy level or orbital. The other noble gases have the same outer shell electron configurations, even though they have different number of inner shell electrons. So all of them will have the same ending. It will have the 2 electrons in the s orbital, the 6 electrons in the p orbital. The only thing that's going to change is the number in front of s and p. Right? If you're talking about energy level 2 neon, well, you're going to see energy level 2. If you're talking about argon, right? Argon right here, energy level 3, you'll see that 3s and 3p. If you're talking about krypton, you're going to see 4s, 4p, and then so on and so on for xenon and radon and element 118. Remember, if you have these 8 electrons, you are unreactive. Why are you unreactive? Because you have 8 electrons in your outer orbital. You don't need any more. So, are you going to combine with other elements? No, you're not. Why are noble gases unreactive? What is it about these noble gases that makes them unreactive? And remember, if you're not in Pear Deck, you should answer in the Google Meet chat. All right, Kevin just got here. So while you guys are doing that, I'm going to change Kevin's attendance. I love the attendance today. I wish we would do it more often. I need you guys to be showing up. America's not here. Melissa's not here. There's still a couple people missing. But this is the best attendance we've had in the last couple weeks. So why are noble gases unreactive? Why are noble gases unreactive? What do they have that all the other elements on the periodic table don't have? There is something special. What is so special about noble gases? What did they say? What happened? They don't have electrons. They are in order. I think we can do better than that, guys. What does noble gases? Why do noble gases? Why are the noble gases unreactive? What do they have in that outer shell? What do they have that all the other elements don't have? How many electrons? It's all about the electrons. Remember, chemistry, according to Dr. Delasses, one of my professors at UTRGV or UTPA, back then what it was called, Dr. Delasses worked a lot with BP. Hold on, give me a second. Ah. Okay, she just had a quick message for me. All right. So, did anybody change their answer? Let's see. Did they change their answer? What? How many valence electrons does group 18 have? Take off that one. How many valence electrons? If we're talking about group 18. How many electrons for group 18? 8. If you have 8 in that outer shell, you don't need a bond with anybody in order to make that 8. You already have it, which all of the noble gases already have. That's what makes these guys unreactive. It's all about the 8 valence electrons, okay? Keep that in mind. 8 electrons. Very good. Very good. All right, it says draw the electron configuration of argon. We're going to do this on Jamboard as a group, okay? So I don't need this guy. I need this guy. I'm going to circle what we're going to be following, okay? When we do this electron configuration, we are only looking at what is circled, okay? So remember, we need to stop here at argon. Everybody see argon? This is where we need to stop, okay? Because this is what we're asking for. So in the box at the very top of the page, what does it say? Argon. What does it say here in this first box at the top? 1s what? 1s2, right? You can see that in the corner. You can see it inside. It says 1s, and in the corner it says 2. So that's what we write. Energy level 2. What comes next? Over here. Can somebody help me, please? Somebody come off mute and just tell me what to write. What does it say here for the second orbital in energy level 2? I know I kind of went over it. It says 2, right? The orbital in blue is the s orbital. What's the little number in the corner? 2. Okay, so that's what we write. What about the next one? We're still in energy level 2, but what orbital are we talking about? What do you see here? Help me out, guys. What orbital is green? I got a lot of students here. Help me out. Oscar, Alexia. What is the next orbital that you see here? 2 what? 2p, right? 2p. And in the corner it says right here 6, so that's what we're going to write. And now we're here in energy level 3. What's my first orbital? What's my first orbital? What letter? I know I'm in energy level 3, but what's the first orbital? H right here. What does it say here? 3s, 2 electrons in there, and then we have 3p6. Oh my God, my handwriting is horrible today. So this would be the electron configuration for argon. 1s2, 2s2, 2p6, 3s2, and 3p6. And if you look at the last part, doesn't it look like the electron configuration ending of neon? Yes, the only thing that has changed is the energy level has now changed. It still ends in 2s and 6p, or p6, sorry. S2 and P6. The only thing that's changing is the energy level that it is in. All right, let's talk about the octet rule. American chemist Gilbert Lewis used this observation. So he saw and he noticed, okay, I see the electron configuration of all the noble gases, what do these elements need to do to get that electron configuration? So he used this observation to explain the types of ions and molecules that are formed by other elements. He called his explanation the octet rule. The octet rule states that atoms tend to form compounds in ways that give them 8 valence electrons, and thus the electron configuration of a noble gas. An exception to the octet of electrons is in the case of the first noble gas, helium, which only has 2 valence electrons. All right, so there is everybody on the periodic table, well, at least mostly everybody, follows the octet rule where you need 8 electrons. Helium and hydrogen, it says here, this primarily affects the element hydrogen, which forms stable compounds by achieving 2 valence electrons. So hydrogen and helium follow what's known as the duet rule. Duet. If you're listening to a duet song, how many people are singing it? You got 2, right? So remember, if you're talking about the duet rule for hydrogen and helium, you're talking about not 2 singers, but 2 electrons, okay? Hydrogen and helium don't follow octet rule because it can't fit that many. Hydrogen and helium only have energy level number 1, which can only hold 2 electrons. They follow what's known as the duet rule. Duet rule, okay? So, and this affects another element, lithium. Lithium, an alkali metal with 3 electrons, is also an exception to the octet rule. Lithium tends to lose 1 electron to take on the electron configuration of the nearest noble gas, helium, leaving it with 2 valence electrons. Okay, so on the left side, this is what lithium looks like before anything happens, before we lose, before we gain, or before we share. Lithium is element number 3. It's got an atomic number of 3. It's only got 3 electrons. And you can see that the first 2 are in the first energy level or the first shell, and it can only handle 2. If you look at that third electron, it's in energy level 2. Well, alkali metals specifically will always, it's a group 1 metal. So that 1 electron will usually get lost. Okay, so it says here, 1 electron is lost. If that 1 electron is lost, that second orbital disappears. It's no longer there because there's nothing occupying it. So what is left? Energy level 1, with 2 electrons, which makes it look like helium. But it's not. It is lithium with just 1 electron missing, leaving those other 2 electrons. Okay? So even though it looks like helium, it really is the element lithium. How do atoms satisfy the octet rule? So everybody else who's not hydrogen and helium and lithium follow the octet rule. There are 2 ways to make an octet of electrons, to make 8. One way is by sharing valence electrons with other atoms. The second way is by transferring valence electrons from one atom to another. So one atom will lose, the other atom will gain, and both of them will make octet. All right, let's talk about the type of atoms and what they have a tendency to do. So the first one says, atoms of metals. So now we're talking about metals. We're talking about the left side of the periodic table, right? Metals will have a tendency to lose their valence electrons and leave them with an octet from the next lowest principal energy level. And I'm going to show you a picture of what we mean by that. Nonmetals. Atoms of nonmetals tend to gain electrons in order to fill their outermost principal energy level with an octet. So metals have a tendency to lose. Nonmetals will have a tendency to gain in order to make octet. Now, it says here, circle the correct answer for each statement. What happens? It says here, atoms of metals, what? Gain or lose. You need to pick one, and you circle the one that you pick. Atoms of metal will gain or lose valence electrons to satisfy the octet. Atoms of nonmetals will gain or lose valence electrons to satisfy the octet rule. Circle the answer that makes this true. So will you say atoms of metal gain, or will you say atoms of metal lose? Pick one. You cannot pick both. You need to pick one. Either circle gain or circle lose. What do you think, guys? What do you remember from the last slide that we said? What happens to metals? What happens to metals? The left side of the periodic table versus the right side where you have metals, non-metals, sorry. Remember, what happened to lithium, a metal? What happened to lithium? Lithium's a metal. What happened? Did he gain electrons or did he lose electrons? What did we say happened to lithium?
Lose.
It lost electrons. So that's going to be true for all metals. Lithium's a metal. It lost. The same thing happens to all the other metals. They have a tendency to lose. So what happened to nonmetals? Gain or lose? What do you think? Metals lost. What happened to nonmetals, Oscar? Say it again.
They gain.
Yes, sir. They will gain electrons. Okay, so you should have circled lose. You should have circled gain. Let's see. No answers. Thanks, Oscar. Gain. You said lose for this one. You said the opposite, Oscar. There it is. There it is. Very good, sir. Very, very good. Correct. All right, let's watch this video. Oh, come on. Oh, there it is.
Ions are atoms that carry a charge, either positive or negative. Let's take a look at oxygen, which is
the internet's slow.
atomic number 8. You see, atomic number 8 means that there are 8 positively charged protons in its nucleus and 8 electrons surrounding it to balance that charge in the case of neutral oxygen, as it says at the bottom of your screen. Neutral oxygen has these two balanced out to be a zero charge. Now, neutral atoms aren't necessarily stable. Stability is met by having an outermost orbital that's full, and oxygen achieves this by picking up 2 extra electrons. So now we see that the outermost or valence shell is full in the case of oxygen, and of course this means that it has 8 valence electrons. Thus we call this the octet rule. An atom is most stable when the outermost orbital is full, which typically means having 8 valence electrons. So now if you look at the bottom of your screen, you'll see that now we're talking about stable oxygen, which has 8 protons, but now 10 electrons total, which means that its net charge is now a -2 because of the addition of those 2 electrons. Positively charged ions are called cations, as in the case of magnesium, which results from a loss of valence electrons. Atomic number 12 for magnesium means that it has 12 positive charges in its nucleus and a total of 12 negative electrons surrounding it. Now those 2 negatively charged electrons in its outermost orbital then are easily lost in the case of magnesium, so that magnesium ion then has a full outer orbital and meets the octet rule, that full outer orbital of 8. And we see...
All right, so I'm going to stop it here. So first off, you have to remember metals. Metals will have a tendency to lose electrons. So if they lose electrons, they will always be considered cations, okay? Losing of electrons leaves you with a positive charge, right? Because you have more protons than you do electrons. All right. And then I always tell my students, look at the T. What does the T look like? Does it look like the negative charge right here or the plus sign, the positive? What does it look like? A plus sign or a minus sign? The T. So remember, the T in cation is for the positive charge that happens when you lose electrons, okay? Now, let's talk about neutral versus stable. Neutral and stable are different, okay? If you have an element that's neutral, that means it has a zero charge, you have an even number of protons and electrons. That is not the same as being stable. Stable means 8 electrons on the outside. Now, what happened here? This magnesium lost 2 electrons. You can see here, there's 2 electrons on the outer energy level. Look at the second energy level and count how many you see. Well, here's 1, 2, 3, 4, 5, 6, 7, 8. If we get rid of these 2 electrons in the outer energy level orbital, it's going to disappear. It's going to disappear, and you're going to see what you see on the right. You're going to see 8 electrons in the outer shell. What happened? I had 12 and 12. I lost 2, so now 12 plus 10 gives me that plus 2 charge. Okay?
See here that now, when we count up protons and electrons, there are an additional 2 protons over electrons, thus giving magnesium ion a net positive 2 charge. In the case of fluorine, we see that it will normally form a negatively charged ion, which is called anions, and this results from the gain, then, of valence electrons. So fluorine is atomic number 9, which means that it has 9 protons and, in its neutral state, 9 electrons for a 0 charge, which means it also has 7 valence electrons and thus easily picks up that 8th valence electron to have its full outer orbital, thus fulfilling the octet rule. And now we see that fluoride ion has 1 additional electron over the protons and thus carries a -1 charge.
Supposed to stop it. Okay, so now we're on the opposite side. Now we're talking about nonmetals. Nonmetals, we know, gain electrons. That gives them a negative charge. That makes them anions. And I always say, guys, look at the N and remember N is for negative, okay? N is for negative. You are a negatively charged ion because you have gained valence electrons. And here again, you have stable versus neutral. On the left, you have your neutral. On the right, you have your stable version. So both of them are fluorine. How do I know they're fluorine? Well, because look at the number of protons. 9, right? 9. I am showing 9. I got 2 plus 7 more gives me 9. But it doesn't satisfy octet. I have a neutral charge. I have 0 charge, but I'm not stable. What needs to happen for me to be stable? I got 7. I need 1 more. That 1 electron comes in, and now I am no longer neutral, but I am stable. How am I stable? Well, look at what happened. I have 8 valence electrons. 1 in red, 2, 3, 4, 5, 6, 7, 8. Now, when I do my overall charge, I got 9 protons, 10 electrons. This is where we get that -1 charge that you see here on fluorine or fluoride.
Is a -1 charge. So press pause at the bottom of your screen and take a moment to answer the following for each of these ions. Are they cations or anions? How many total electrons do they possess? And how many valence electrons do they possess?
All right, and we're going to do this real quick. Which ones are my cations? Which ones are my cations? Where do you see that T for positive, right? Where do I see that positive sign? Which one of these 4 is considered a cation? I'm watching the chat. I don't see anything. Alexia, Mario, where do you see that positive charge? What elements have a plus charge for that cation? Sodium, Na, which one else? Which one else has a positive charge like you see here? Hydrogen. Thank you, Irvin, Oscar. Perfect. Okay. So then that makes oxygen and chlorine my anions, right? Okay. Now the second question, how many total electrons? Well, let's see what happened before I lost and I gained. So I need a periodic table. Here it is. Sodium. Right here. It had, before it lost and it gained, 11 electrons, 11 protons. What happened if you see a plus sign? Did it lose or did it gain? Metal or non-metal? What happened if I see a plus sign? I know it's a plus 1, but does that mean I gained one or did I lose one as an atom? What does the plus sign mean? Think about it. Cations. It's a metal. What do we know about metals? What did we say in the last slide that happens to all metals? You said it earlier, didn't you, Oscar? Oh, okay. They sent to lose. So this guy lost. He lost 1 electron. So if originally he had 11, how many total does he have now if he lost 1? 10.
10.
Very good. Now, how many valence electrons? We know that they lose and gain to make 8. So what should all of them have as far as valence? 8. Okay, so the only question we really have to answer is the first and the second one. Oxygen. Oxygen originally had 8 electrons. What happened? Now, how many does it have now if you see a -2? For the first one, we said, oh, if there's a plus, that means it lost. If there, and this is the opposite. This means lost. What does negative mean? Gain, doesn't it? So if you originally had 8 and you gained 2, that's a total of 10. Be careful, Oscar. You're already subtracting. I saw that 6. Don't think I didn't see it. What about hydrogen? Hydrogen, element 1. What happens here for this guy if he's got a +1? How many total electrons? Before it only had 1. It lost 1. So what's my number? Settle, right? 0. 1 minus 1, 0. 0 total electrons. Chlorine. Chlorine is element 17. Element 17. What's my total? Before it lost and it gained, it had 17. How many now when you have a -1 charge? Do you still have 17? Do you have 16 or do you have 18? You add 1, right? So what's 17 plus 1? 18. Thanks, Oscar and Irvin.
All right. Okay, so for sodium ion, you see it's positively charged, which means it's a cation. Now, if we do our orbital diagram for sodium in the neutral state, we see that it has that 1 valence electron on the outer ring. That 1 valence electron is easily lost to fulfill the octet rule and give sodium ion a stable outer orbital. And we also see that this results in 1 additional proton over electrons, giving it a +1 charge. So there are a total now of 10 electrons, and only valence electrons being counted, we see that it has 8, which of course is the reason it lost that 1, is to fulfill the octet rule and have the 8 valence electrons. For oxygen ion, we see that it's an anion because it's negatively charged. And looking at its orbital diagram, we see that it has those 6 valence electrons in its neutral state, and oxygen likes to pick up those additional 2 electrons to give it a full outer orbital. And thus, with the addition of those 2 electrons, it now has a total of 10 electrons, but again, fulfilling the octet rule and giving it an 8 count for its valence electrons. Hydrogen ion, in this case is a cation because it has a positive charge. We see in its orbital diagram one positively charged proton at the center and one negatively charged electron surrounding it. That one lonely valence electron is often lost, thus giving hydrogen ion a net positive 1 charge. Total electrons are 0, and of course total valence electrons are 0. Finally, with chloride ion, we see it has a negative 1 charge, thus it's an anion. And when we do its orbital diagram, we see 2 electrons in the first orbital, 8 in the second, and a 7 valence electrons in its neutral state to add up to 17 to balance its atomic number. So chloride likes to pick up that additional electron in its outermost orbital, giving it a full octet, and thus having 1 more electron than number of protons and giving it a negative 1 charge. Thus, total electron number is 18, and valence electrons is again 8.
All right. Thank you. All right. I think we're gonna. Okay, that's it. In summary, atoms form compounds in ways that give them 8 valence electrons. Metals will have a tendency to lose electrons. Nonmetals will have a tendency to gain electrons. These are the questions that we're going to tackle right now. Okay. All right, we're going to skip question 1. I don't like it. I don't think that they answered it clearly in the text. So number 2, let's skip number 1. Why is this configuration important? And they're talking about the electron configuration of a noble gas. Why is the electron configuration important for noble gases? What does it say here in this paragraph? They're talking about the noble gas neon. Why is that electron configuration important? What does it give us?